Hello students, welcome back. We went through a couple of examples on polynomial congruence. First, a motivating example. We started something trivially simple, a little bit harder, and then even more complicated. The first reduction from C to lowercase is through the Chinese remainder theorem. If you have multiple prime factors with whatever powers, using the Chinese remainder theorem, we can decompose one congruence into several simpler congruences. Here we have two prime factors, 5 and 2, so we have just two congruences. If you have, say, 15 prime factors, then we're going to end up with 15 congruences, or with modulo p to the k power form. Now, how do you reduce modulo p to the k power form? We have some idea here, but redoing these kind of things from scratch is a bit too cumbersome. It works, but too cumbersome. So let's focus upon a theorem, Hensel's theorem, which has a restriction, but otherwise pretty good. Let P be a prime and R be the solution of the polynomial congruence. The base case, f of x is congruent to 0 modulo P. In other words, f of R is congruent to 0. And here's an additional condition. The derivative f prime of R is non-zero modulo P. Then the solution of the kth generation, f of x is congruent to 0 modulo p to the k power. Let's name it rk as the solution. Then it is obtained recursively like this. Rk is rk minus 1 minus f of rk minus 1 times f prime of r inverse. And that inverse exists because f prime of r is non-zero modulo p, and this inverse is modulo p. The base case is the same as R, and then R will give you R1, and R1 will give you R2, R2 will give you R3, R3 will give you R4, and so on, up to Rk for modulo p to the k power. Yeah, this f of R inverse is a multiplicative of inverse of f prime of R, but it's modulo p. And then we went through one example problem right here. And let's do it again. This time let's work on this thing here. For that purpose, let me copy and paste this recursive equation here. All right. Okay, let's begin. So here we don't need this anymore. So let's work on this. Okay. The base case is 3, modulo 3, and that's even easier. We have only 3 numbers to consider, 0, 1, and 2. And all those are easy. Plug in 0, that's trivial. Plugging in 1, in place of x, just put 1. And then plugging in 2, we have negative 1 in place of those x, so that's all easy. And it turns out g of 1 is 0, modulo 3. Okay, all right, and then let's apply Hensel's theorem. So the base case, this R value is 1, and then we want f prime of 1 inverse, or g prime of 1 inverse. Well, okay, let's calculate the derivative. So what's the derivative here? What's the derivative? That's it, isn't it? Yeah, that's a derivative computation. And then I'm plugging in 1 in place of x. So g prime of r is g prime of 1, and that'll turn up at 2. So its inverse is 2. 2 times 2 is 4, and that's congruent to 1 modulo 3. So, all right, we have this inverse, multiplicative inverse of the derivative evaluated at r, which is highlighted in red, and then we need some recursion as a matter of fact. We have to go to R3. So from R to R1, all right, R1 is same as R, so that's 1. And we have to get to R2, and then we have to get to R3. Okay, so R1 is the same as R, so that's 1. And G of R1, again, do your computation. That's 0. Okay, all right. And then let's find out R2. That's 1, and that's 0. So you see, that's R1, that's 1, and G of R1, that's 0. And then this one is 2, but it does not contribute this time because multiplied by 0, it'll disappear. So R2 is 1 again. All right, next R3. We have to do this recursively again. So R3 and R2, we have it. G of R2, we need that. So okay, let's calculate G of R2. So G of R2 is, well, plugging in 1, and then that's 9 modulo 27. You see, modulo 9, 1 plus 1 plus 7 is 0, but mod 27 is not 0, it's 9. So we have 9 right here, and then red is 2. So we have the final computation here. R2, which is 1 again, and G of R2, green, and the G prime of R inverse, which we did in step 1. And that turns out to be 9 times 2. So 1 minus 9 times 2, negative 17. That's congruent to 10 modulo 27. So that should be your answer. If you started from multiple zeros in step 1, then for each 0, we will have this kind of reduction, recursive reduction. But we started from unique 0 here, so we have only unique solution there. By the way, here's verification through Mathematica, and I calculated everything here, and let's see, mod 3, mod 9, mod 27, and then these are the zeros. Yeah, right here, 1, 0, and then 1, 0 again, and this time 10, 0. So, applying Hensel's theorem twice. No big deal, right? Let's do this one more time. X cubed plus x squared plus 2x plus 26 is congruent to 0, modulo 343. 343 is 7 to the third power. So we begin with mod 7, and as usual, brute force method. Plug in x as 0, 1, 2, 3, 4, 5, and 6, and it turns out f of 2 is congruent to 0. Okay, it is a bit cumbersome if this modulus is big, and 7 is a bit bigger, so it was a bit harder. If you have something like mod 19, it's gonna be really troublesome. Mod 63 is gonna be worse. Anyway, we have it. F of 2 is congruent to 0, so R value is 2. We have it. So applying Hensel's theorem, for R is 2. Oh, excuse me, we need the derivative computation first. Okay, let's do the derivative computation. We have 3x squared plus 2x plus 2. That's the derivative. And then we are plugging in R in place of this and that. And then R value is going to be, wow, why do I have T here? R value is going to be 2. So if you plug in 2 squared and then have 2 again, and run your calculator, you're going to get -2 plus 4 plus 2, end up with 4 modulo 7 according to my computation. Is that right? There's one easy way to check. Modulo mod operation. Yep, it's 4. Detail is left to you. So this computation is 4. So if you divide this number by 7 and take the remainder, it is 4. With paper and pencil computation, it's going to be cumbersome. So I cheated. I used Mathematica. But given sufficient amount of time, everybody will be able to do that. And 4 inverse will turn out to be 2. Let's see, 4 times 2 is 8. And 8 is congruent to 1 modulo 7. Oh, come on, I keep failing. What's with this mouse? Okay, all right. That's 2. 2 will go here. All right. Now we have to go to R3, isn't it? We have 7 to the 3rd power. We need R3. R value will give you R1. And then in order to find R2, we're going to need R1 and f of R1. So let's find R1 and f of R1. R1 is 2, same as R. And f of R1, yeah, we'll have to plug in x as 2 into this and run your computation, modulo 49. So, do you feel okay about this computation? 42 modulo 49, so reduce to -7 so that the next computation is slightly easier. So this computation, this one here, will go right here in the next step. Let's find R2. R2 is going to come in from this, R1 minus f of R1 times the inverse, highlighted in red. So R1 is 2, and f of R1, as you calculated, is -7. And then this inverse, which we calculated in step 1, is 2. So 2 minus -7 times 2, so 2 plus 14. So we have 16. Okay, all right, we have R2. Now we need R3. For R3, we need R2 minus f of R2. Let's do f of R2. F of R2 is, well, let's just plug in 16 and then run your calculation. 16 to the 3rd power plus 16 squared plus 2 times 16 plus 26 modulo 343. And I have a confession, I didn't do this computation by paper and pencil method. I just used Mathematica. 294, so you end up with -49. It's got to be right. Let me copy and paste this thing. Yes, 294, so it's congruent to -49. So this is -49, as you calculated, and this one is something we calculated in step 1. So 49 goes here, and then 2, do your computation, you get 114. So basically we are using Hensel's theorem twice. And here's a verification. Yeah, we indeed get 114 if you do that brute force computation up to 7 to the 3rd power everything. Now if you can do it 3 times, you can do it 4 times or 5 times, just a matter of time. And then combining those with Chinese remainder theorem, again, matter of time.